we are going to talk about lists. Lists are the fundamental data structure of a functional programming language. There's a functional programming language called Lisp, which is the first functional programming language invented, which only has lists. All of it is built around lists. It's a very powerful and very flexible data structure, and it's the only thing you really need to get things going, to write real programs, is lists. Everything else is a convenience. It makes writing certain programs more convenient, but they can be written just with lists if you really want to do it. So a list is just a sequence of values. So first I want to spend some time to see why are lists so important. So suppose that we want to write a function that adds a bunch of numbers. Yeah. So this is the function that adds two numbers. Yeah. Let's call it add 2 because it adds 2 numbers. And now let's write the function that adds 3 numbers. X, Y, Z. So it's going to be X plus Y plus Z. But now, suppose that I want to keep going. Y plus Z plus U. Okay. So as an exercise, do a function like this that adds 100 integer. Yeah, it's going to be quite boring. You run out of letters. You start to think maybe I should have used x1, x2, x3 instead. So we want to do something that's a little bit more clever. So let's re-implement it in the following way. We still call this one add 2. So I'm going to put some comments here to explain what I'm doing. So I'm still calling this add 2 x plus x, y, x plus y. But now add 3 of x, y, z, I'm going to say x plus, well, I have already implemented the addition of 2 numbers. So I can just call add 2 instead with y and z. Yeah, see what I've done? Add 4 x, y, z, u equals x plus add 3 of y, z, u. So you can see this has a nicer pattern to it, because let's call them like this: x1, x2, x3, dot dot dot. This is no longer OCaml. I just put this is no longer OCaml. This is just to show that it's a long list of arguments from x1, x2 all the way to xn. Then I can write x1 and then add n minus 1 and then x2, x3 and so on to xn. So I'm going to put it in comments because this is not actual code. Okay, so this is a little bit nicer, because imagine here I've done a simple operation plus, but suppose that the body of the function was not just addition but something more complicated, and then I only have to do it once, the body of the function, and then I just call the function to do it on the smaller set of arguments. Okay, but anyway, it's not a nice way of doing it, because Because of what? Can you see kind of some shortcomings with this? So I started trying to add a bunch of numbers, but what's the limitation here? Yeah. So first of all, it has to be fixed. My n has to be fixed. Second, I have to re-implement it. If I want to go n plus 1, I have to implement another one, and then another one, and then another one. So for every let's say size of arguments, I have to have a different function. And then when I call it, I have to look, I have to know how many functions, how many elements I'm going to have, and then call the right function. So it's very restricted, very awkward, only suitable for small n. There's no way I can write, I can sum up 1,000 numbers like this, or 1,000,000 numbers. It would be quite insane to do it. And you know, in programming, you often need to sum 1,000,000 numbers. If you have a database and you want to have a long list of data and you want to do some operation over it, it's not unusual. I mean, it's not impossible to have to work with a list of 1,000,000 numbers. So so let's look again at another variation on this, which is still going to be awkward, but I'm going somewhere with it. So first I'm going to introduce another bit of syntax. So the way I'm going to deal with OCaml in this module, whenever I need a little bit of the language, I'm just going to introduce it on the fly. It's not going to be a big lesson about all the features of OCaml. We only introduce the features when we need them one by one. Just like you can define functions and values in OCaml, you can also define types. So you can give names to types. So let's call P2 a pair of integers. Yeah? So it's a pair of two integers. And let's say type P3 equals int star int star int. Yeah? So it's a tuple, P3, it's a tuple with 3 values. But I'm going to do the same trick as we did with add. So instead of saying int times int times int, I'm just going to say int times P2. And type P4 is going to be int types int, a product of int and P3. Okay. If you're still a bit kind of unsure about what does this star means, this is not multiplication. Because multiplication is something that we do to values, such integers, so you can do 3 times 7. But this is applied to types. So this is a tuple. This is the pair. The first element of the pair is an integer. The second element of a pair is a P3. And what is a P3? Is a pair. The first is an int. The second is a P2. And what's a P2? It's a pair of ints. So now let's write our functions now, which they take, instead of taking an argument, instead of taking a list of the arguments, they're going to put all the arguments together in a tuple. And it's going to take that as an argument. So let's re-implement them. Let add 2. So now P2, sorry. So xy. So I call it xy because it's a pair that has 2 things in it, an x and an y. So we pattern match xy and we pattern match xy against its components. We get the x and the y. Yeah? So here at the bottom, so here at the top I have a file, and here at the bottom I have the interactive environment. So if I do add 2 of 3 and 4, see, I get 7. And the type of add 2, you can see it here. It takes a pair of ints and it produces an int. Add 3, I'm going to call it XYZ because it has, really, I know that it's a tuple of 3 things, an X, a Y, and a Z. So again, I'm going to match the X, Y, Z with, so now what's the first component going to be? The first is going to be X, and the second one? What's a good name for it? You can call it anything, because this is just, we're introducing a new variable name. But to keep it intuitive, what would be a good name for the second variable? Any suggestions? Let's try another one. YZ, yes, exactly. Because we're breaking a tuple of 3 things in 2. So the first part is going to have only one thing, the X, and the second part is going to have 2 things, the YZ. So here I get X plus, so I want to calculate the sum of all of them. But I already know how to calculate the sum of YZ. So it's going to be, how do I calculate the sum of YZ? Add 2 of YZ. So let's see how it works. Add 3 of 1, 2, 3. Why it didn't work? Any suggestions? Yes? Yes. So you see, I'm going to line up this error message here so that we can see what we fed into the expression and what it expected. It expected a pair of triples associated to the left, associated to the right, but when you write it like this, it's associated to the left, so that's why the brackets are not shown anymore. So, yeah, these are 2 data types that are isomorphic. So it doesn't matter how you put the brackets in order to have the same information, but they're different. They're isomorphic, they're not equal. So we have to do the brackets properly and try again. And now it works. So let's add 4 X, Y, Z, U equals match X, Y, Z, U with, we get the first one and then the rest, X plus add 3 of Y, Z, U. So you can see here the signature. Yeah, it doesn't actually tell me P2, P3, P4. It resolves those names into their definitions. So if I try to do add 4 of 1, 3, 5, 7, it works. But this is starting to get nicer. Because now whenever I want to write my function let add n of x, and now x is a big tuple. It's a big tuple that has many elements. So let's call it L because it's really like a list. Yeah. So it's a big tuple which is going to have how many elements? Since we're calling add n elements. Yeah. But now I can write all in a uniform way. Match L with, I can always take the x, the first one, and then I can take the rest. And then it's going to be x plus add n minus 1. So this is, yeah, again, this is not OCaml, of the rest. So you notice how this is different from the pattern before. When we were feeding the arguments at a list, we had to write n functions, all of them, with a different kind of signature and a different kind of implementation. Here, we still have to write n functions, but the n functions are now very similar. They're always going to say add n. They're going to pattern match taking the first element and the rest, and then it's going to call x plus and then the previous function on the rest. So this is doing it in a very uniform way. So it's still not good. It's just slightly better. Yeah. Why is it? It's slightly better. It's a little bit more uniform. It's a little bit nicer, but we still have the same problem. We're restricted. We have to implement a different function for each tuple size, which is very restricted, very awkward, and only suitable for small n. And this is why we need lists. Because what is a list? A list is like a tuple, but of a size that's not fixed. That's exactly what it is. So think of lists as tuples of unknown size. Okay, so now a little bit about the list syntax in OCaml. To write a list of elements in OCaml, you go open square bracket and then a bunch of things that you put in the list, and they have to be separated by semicolon, like this. And note the type, int, list. Yeah? So list, it tells you this is a list of integers. And the reason why it tells me it's a list of integer is because I can make a list of anything. There's only one restriction. I cannot do this. I cannot do this because in a list, everything has to have the same type. So here, let's amend this definition. Think of list as tuple of unknown size and homogeneous type. So homogeneous means everything has the same type. Okay? So this is not possible. But you can put anything in a list. So you can make something like this. So this is, the brackets here would go like this. And you read it from right to left. So it's a list, and every element of the list is a list of integers. That's fine. You can put anything. The list can go over any type. Or this. It's a list of functions. And here it also tells me some information about the functions, but I don't want to go into that now. I'm just going to change it slightly here to use product. Let's see if it's bad. No, it's still not good. This. I think I need to put some brackets. Yes, that's what I wanted. So without the brackets, the parser got a bit confused. So the first function, it's a function that takes x, it produces x. The second function, it takes x and produces 1 times x. That's really a bizarre function to have. But anyway, it tells me that I have a list of functions that take an integer and produces an integer. I can have a function of anything. And this is the empty list. And look at the type of the empty list. It's a list of whatever. So here, when you see in a type signature, this quote character, it's a variable type. So it's a type that's not known. So that means it's a list of something. It's a list of something, but I don't know yet a list of what. And the same thing happens if I define the identity function. So it's a function that takes an argument of some type, which I don't know, and produces a value of the same type, which I don't know. Or this one. The pairing function. It takes some A, which I don't know what the type is. It takes some B, which I don't know what the type is, and returns their pair. Yeah. So this is called polymorphism. It's spelled like this. So compare it with the other word that you learned last time called isomorphism. Polymorphism. Isomorphism means the same shape. Polymorphism means many shapes. So lists are polymorphic because they can have many shapes. So this is a polymorphic list. It's a list that can be seen as having many shapes. This is a list of integers. If you wanted to write the empty list of integers, that's what it looks like. But an empty list of functions also looks the same, or an empty list of tuples also looks the same. They're all empty lists, but I can make them of any type. That's why it's called polymorphisms. Okay, now you have to be quite careful when you use lists of possible syntax errors. So what do you think is the type of this list? It's a list of what? Who thinks it's a list of integers? Who thinks otherwise? Okay, what do you think it is? Okay, who thinks it's a syntax error? Who thinks yet a different thing? What do you think? Yes, indeed. It's a list of triples. So that's a very easy mistake to make. If you accidentally write comma instead of semicolon, it still makes sense because comma is used in triples. It's used in pairs, and a list of pairs is perfectly fine. And even if you do this, what is this going to be? Yeah, this is a type error. Why is that a type error? Somebody else? Why is it a type error? It's not homogeneous, exactly. It's got both tuples and singles. So that's the good outcome. When you get a syntax error, it's good because you can go and fix it. If you don't get a syntax error, then it's a lot worse because you actually introduce a value. And you will get an error at some point, but further down the stream. And you will go like, oh, why is this an error? Why does it say it's sending a triple when I'm clearly trying to send just a list? So that's something to be careful about. But other than that, it's very, very flexible. So this is a list that contains the empty list. So this is not the empty list. This is a list that contains the empty list as an element. Okay? How do we get to the data inside lists is with pattern matching. And I'm going to copy paste this so that you remember. So I have a term of comparison from tuples. So in tuples, it's something like this. Match the tuple with, and then it's the pattern. So the pattern of a tuple, it's always bracket, sorry, the pattern of a pair. It's bracket, the name, the first name, comma, the second name, bracket. So for list is, I'm going to call it X's. That's how you read it, X's, because it's a bunch of X's. Sorry. And here, the pattern matching goes a bit, it's a bit more complicated than in the case of, let me put that. It's a bit more complicated than in the case of pairs, and here's why. In the case of pairs, we always had only one pattern. A tuple, a pair, has only the two components, always the same. But a list can be also empty. So that's a special case. Yeah. So the list has this special case. So I can say, that's how I do the two special cases. Vertical bar. So that's a new bit of syntax that's used in pattern matching to distinguish between patterns that have cases built in. So I can get the empty list, and here you write code for when the empty list. And then the other case is when my list is not empty. And when my list is not empty, the way OCaml breaks it down, it's always in the first element, which is called the head, and then this symbol, colon, colon, and then the rest of the list, which is called tail. And here you put code for when we have a head and a tail. So let's see how it works here. So if I say, for example, match 1, 2, 3, 4 with bar and this, so get the, I'm just putting some random values there just to see the execution. So if I'm just going to say, okay, let's say empty. Otherwise, if I have a head and a tail, I'm going to say not empty. Yeah. So now it says not empty because it goes on the case. So I'm going to do it step by step here. So here, pay attention. You have a question? No. No, there are any names that you can, they're names of variables. Yeah. Let's call them, just for the sake of making so that it's clear it's not a keyword, I'm just going to call them H and T here. So how do we evaluate this symbolically? Well, the first thing that you do is decide here what branch you take. And this branch is decided strictly by pattern matching. So can we pattern match 1, 2, 3, 4 against this? No, you can't, because this is empty and this is non-empty. So it doesn't, no, it doesn't work. So the first step is, since this case is impossible, it's going to be discarded. Then, can we pattern match 1, 2, 3, 4 against HT? Yes. H becomes 1 and T becomes 2, 3, 4. So that means we're going here. But here we reached a value, so we stop. When you reach a value, you just stop. There's nothing more you can do. You just produce that value. I computed the word not empty. So let's do our add-n function with this better syntax on lists. So let's comment this out as well because it gets the parser confused. So one of the good things about using an Emacs mode is that having this automatic indentation, when you press tab, it does automatic indentation so that things are lined up nicely in your code. And if you forget the bracket or you have some stuff that doesn't belong here, you can usually see the fact that the indentation becomes a bit weird. So you can, that's what I did. It was like, why is it, I'm trying to indent it and it goes here. And the reason was, somewhere up, I had just a semicolon instead of double semicolon. So now I fixed it and it's fine. So let's add 0. Okay, so what I'm going to implement, sum up the elements of a list of size less than n. So if the size of my list is less than n, I'm going to produce the size. Otherwise, I'm going to produce just 0. So add 0. So that means a list, an empty list. So first I have to check if it's an empty list. So because it's an empty list, the sum of all the elements over an empty list should be 0. And otherwise, well, this is an add 0, so it only works correctly for lists of size 0. So I just produce an arbitrary value, 0. Yeah? And I'm going to put this actually all on one line, because it's quite short. Now, lists of size up to 1. Now, the first case is we're going to do something for the empty list and something for the non-empty list. If it's the empty list, well, if it's the empty list, I know it's always going to be 0 because summing over the empty list, it's always 0. But now, when I pattern match with head tail, I take the first element and the second element, the tail, is going to have what size? 0. So I can use the previous one. So I can do head plus add 0 of tail. Now for size 2, if it's empty, we get 0. Otherwise, yeah. Otherwise, I always I can always do this. If I want to add up to n elements, well, the empty is always 0. Otherwise, I have to call the one that's less than it. So, so we introduce some new syntax, the list and the new concept, and we have, it doesn't look like we achieved much, but we actually achieved something. So let's look at the signatures here. Look at our functions, add 0, add 1, and add 2. The signature of add 0 is going to, it's a bit, it has this polymorphic type, but a polymorphic type can be considered to be any type. So we can think of it as being any type. So it's any list to int. Add 1 is list of int to int. Add 2 is list of int to int. If I add another one, add 3 is list of int to int. So can you notice something as opposed to when we were working with tuples? Well, we were always producing an int there as well, but let's look. Let's look here. So let's look at their signatures here. How do they compare to the signatures that when we use list? Anybody sees the difference? Yes, so that's one thing, but there's something more, it's something a bit even better. Exactly. So with the list implementation, the signature of these files, of these functions, it's always exactly the same. See? Except for the case of the empty, but let's just ignore that for now. But look at add 1. Add 2, add 3, they have exactly the same signature, whereas here, the signature was not the same. So why is this convenient? It's convenient because now if I call add 3, it works. It means lists of up to 3. Yeah? So I don't have to call add 1 and add 2 and add 0 again. I can always call the longest thing that I've implemented. So add 3 of 1, 2. See, it works. It works for 0. Add 3 works for 0 elements, 1 element, 2 elements. Whereas when you had them as tuples, you had to look at the size and call the one with the right type. And now the only problem is that we still have this kind of fixed n. And this is where a bit of magic kicks in. If I could only do this, to define the addition over the summing up of the elements of a list like this. If it's empty, call get 0. If it's not empty, take the sum and add it to the sum of the rest of the elements. If I try to do this, it says, it doesn't work because now this function add is calling this function add, which hasn't been defined. It's a self-reference. Yeah, so going back to the idea of self-reference, this function is trying to use itself. This is how mathematics came crumbling down because of logic. But with programming, we don't have a problem. We just have to tell it by adding this little keyword, rec, that we allow this function to call itself. And that's the little bit of magic that makes everything work. It's called recursive function, and that's what I'm going to talk about next lecture. Thanks.